Alright, so in this video we're going to look at problem number 5. It says consider the helix curve described by the vector function r of t, which is equal to capital R cosine omega t, comma capital R sine omega t, comma capital R omega t, where capital R and omega are positive constants. Part A asks us to sketch the graph of this curve. Alright, so we're going to approach this in much the same way we've solved some of the other problems on this worksheet. We're going to start out by noting that the I and the j components satisfy this equation x squared plus y squared is equal to r squared, and that follows from the Pythagorean identity. And so that implies that our curve lies on the cylinder with the equation x squared plus y squared is equal to r squared, right? So this is the cylinder of radius r, and its axis is the z-axis. So our curve lies on the cylinder, and now if we think about projecting our curve onto the xy plane, well, the I and the j components are parametric equations for the circle of radius r in the xy plane centered at the origin. Okay, so as we let t increase, our curve will wrap around this cylinder. And now looking at the z-coordinate, since r and omega are positive constants, z is an increasing linear function of t. Okay, so if you put this all together, as we let t increase, we're going to wrap around the cylinder following this circular helix curve, right? This is really similar to problem number 3 on the circular staircase. Okay, so the rate at which we're increasing our height above the xy plane here is constant because, again, z is a linear function of t. Okay, so now let's look at part B. It says compute the velocity and acceleration vectors for this curve and interpret your results in light of your sketch from part A. Alright, so with the velocity vector, we're just going to differentiate the position vector component wise, and note that from the I and the j components we're going to pick up factors of omega from the chain rule. So we get negative r omega sine omega t, comma r omega cosine omega t, comma r omega. Now for the acceleration vector, we're just going to differentiate the velocity vector component wise, and again we'll pick up factors of omega from differentiating the I and j components. So that gives us negative r omega squared cosine omega t, comma negative r omega squared sine omega t, comma 0. You can see here we're differentiating the constant r omega. Alright, so now it says to interpret your results in light of your sketch from part A. Well, to begin, let's think about projecting everything onto the xy plane. Okay, and so if I look at the acceleration vector, okay, note that the I and j components of the acceleration vector are the same as the I and j components of our position vector, except we have this factor negative omega squared in front for the acceleration vector. Okay, so if I look at everything projected on the xy plane, what that implies is that the projected acceleration vector will point in the direction opposite to our projected position vector, and so in turn our acceleration vector when projected on the xy plane will point directly towards the center of this circle. Okay, so that's really similar to what we saw in problem number 3 with the circular staircase. Okay, now if we lift up to the circular helix in R3, since the k component of the acceleration vector is 0, that implies that the acceleration is always horizontal. So in other words, it's always parallel to the xy plane. Okay, and since we're seeing when we project onto the xy plane in particular, the acceleration vector points directly towards the center of this circle. Okay, when you lift up to R3, that implies that the acceleration vector will always point directly towards the z-axis. Okay, cool. So how about the velocity vector? Well, we know that the velocity vector always points tangential to our path, okay, in the direction of increasing t, right? So as we increase t, we're moving up along our helix curve, right? So if I think about driving along this road late at night, the velocity vector here in blue is pointing in the direction of my headlights, right? Now also note that the k component of the velocity vector is constant. So that implies that the tilt of the velocity vector above the xy plane is always the same. It's always this r omega k vector. Okay, great. Well, now let's check out part C. It says to compute the length of the curve as t varies from 0 to 2 pi over omega and interpret your result. Okay, well, if I'm going to compute the length, I'm going to start out by computing the speed, right, of a particle moving along the helix as described by this position vector r of t. So I want the magnitude of the velocity vector, so I take the square root of the sum of the squares of the components of the velocity, so negative r omega sine omega t squared plus r omega cosine omega t squared. From the Pythagorean identity, that comes out to just be r squared omega squared, and see here I'm adding on from the k component of the velocity vector the square of r omega, so in fact we have 2 r squared omega squared, which simplifies to the square root of 2 times just r omega. Okay, so note here, right, since r and omega are positive constants, right, that our speed, in fact, as we move along this circular helix curve, is constant. All right, so now to compute the arc length, okay, well, we're letting t vary from 0. We're going to be located right here along the positive x-axis when t is 0, up to when t is 2 pi over omega. Okay, now the period of our sinusoidal waves for the I and j components is 2 pi over omega. So that means, right, we're going to complete one complete wrap around the cylinder, and z, the height, will increase from 0 up to, well, r omega times 2 pi over omega, which is really just 2 pi r. And note here that that's actually just the circumference of the cylinder. But in any event, we're finding the length of this yellow arc here. All right, so to do that, I'm going to integrate the speed as we let t vary from 0 to 2 pi over omega. And as we just computed up here, the speed is constant. It's just the square root of 2 times r omega. So integrating, we get the square root of 2 r omega t, and now we evaluate. And so if you plug in 2 pi over omega here, this simplifies to 2 pi r times the square root of 2. Okay, now the problem also says to interpret your answer. Okay, now there's an interesting way to interpret this. Notice 2 pi r, that's just the circumference of the cylinder. So where's the square root of 2 coming from? Well, if I slice the cylinder vertically along this line right here, okay, and I lay the cylinder out flat, what am I going to see? Well, first notice, right, that the height here, as we go from our starting point at t equals 0 up to our ending point at t equals 2 pi over omega, as we already noted, where you plug 2 pi over omega in for t into the z coordinate, you just get 2 pi r. So the height here, which is right here, is 2 pi r. It's just the circumference of the cylinder. And see, if I cut the cylinder and lay it flat, okay, the width here that we're going to see is the circumference, right? So it's also 2 pi over r. And now what's going to happen to this portion of the helix, right, when you cut and lay it out? Well, it's going to simply be the diagonal of this square. And the length of each side of the square is the circumference of the cylinder, 2 pi r, so that particular arc length is 2 pi r times the square root of 2. That really just follows from the Pythagorean theorem, so kind of cool. But in any event, that does it for this question, and I'll see you in the next video. Thanks so much.